Welcome to this series of supply chain lectures. I'm Johannes Vermorel, and today I will be presenting Getting Started with a Quantitative Supply Chain Initiative. The vast majority of the data crunching supply chain initiatives are failing. Since 1990, most companies operating a large supply chain have been launching major predictive optimization initiatives every 3 to 5 years with little or no results. Nowadays, most teams, supply chains or data science, starting yet another round of predictive optimization, typically framed as forecasting project or as an inventory optimization project, don't even realize that their company has already been there and done that and failed, possibly half a dozen times already. Going for yet another round is sometimes driven by the belief that this time it will be different. But frequently teams are not even aware of the many failed attempts that happened before their time. An anecdotal evidence for this state of affairs is that Microsoft Excel remains the #1 tool to drive supply chain decisions, while those initiatives were supposed to replace spreadsheets with better tools. Yet nowadays, there are still very, very few supply chains that can operate without spreadsheets. The goal of this lecture is to understand how to give a chance of success to a supply chain initiative that intends to deliver any kind of predictive optimization. We will review a series of critical ingredients. Those ingredients are simple, and yet they come very frequently as counterintuitive for most organizations. Conversely, we will review a series of anti-patterns which almost guarantee the failure of such an initiative. Today, my focus is on the tactical execution of the very start of a supply chain initiative with get things done mindset. I will not be discussing the grand strategic implication for the company. Strategy is very important, but I will be discussing this matter in a later lecture. Most supply chain initiatives do fail, and the problem is barely ever mentioned publicly. Academia publishes tens of thousands of papers per year, boasting all sorts of supply chain innovation that can be supply chain frameworks, supply chain algorithms, models. Frequently, the papers even claim that the innovation has been put to production somewhere. And yet, my own casual observation of the supply chain world is that those innovations are nowhere to be seen. Similarly, software vendors have been promising superior replacement for spreadsheets for the last 3 decades. And again, my casual observation indicates that spreadsheets remains ubiquitous. We are revisiting here a point that was already touched in the second chapter of this series of supply chain lectures. Simply put, people have zero incentives in advertising their failure, and thus they don't. Moreover, as companies operating supply chains tend to be large, the problem is typically compounded by the natural loss of institutional memory as employees keeps rotating from one position to the next. And thus, while neither academia nor vendors acknowledge this rather dismal situation, I propose to start with a short survey of the most frequent root causes for failure from a tactical execution perspective. Indeed, those root causes are typically found at the earliest stage of the initiative. The first cause for failure is an attempt to solve the wrong problems. Problems that are inexistent, problems that are inconsequential, or problems that reflect some sort of misunderstanding about the supply chain itself. Optimizing percentages of forecasting accuracy is probably the archetype of such, I would say, incorrect problem. Indeed, reducing the percentage of forecasting error do not translate into extra euros or dollars of return for the company, not directly at the very least. And the very same sort of situation happens when a company is chasing specific service level for its inventory. It's very rare to have any, I would say, euros or dollars of return to show for it. The second root cause of failure is the use of ill-fitting software technology and ill-fitting software design. For example, ERP vendors invariably try to use a transactional database to support such a data crunching initiative because it is what the ERP is built on. Conversely, data science teams invariably try to use the bleeding edge open source machine learning toolkit of the day because it is a cool thing to do. Unfortunately, ill-fitting pieces of technology typically generate an immense amount of friction and a lot of accidental complexity as well. The third root cause of failure is an incorrect division of labor, an incorrect organization. In a misguided attempt to leverage specialists at every stage of the process, companies tend to fragment the initiative over way too many people. For example, the data preparation is very frequently done by people who happen not to be the one in charge of the forecasting. And as a result, garbage in and garbage out situations are all over the place. More generally, diluting the responsibility of the final supply chain decisions is a recipe for failure. One item that I have not listed in this short list as a root cause is bad data. Indeed, data is very frequently blamed for failures of the supply chain initiatives, which is all too convenient as data cannot exactly respond to those accusations. However, data is usually not at fault, at least not in the sense of struggling with bad data. The supply chain of large companies went digital decades ago. Every item that is purchased, transported, transformed, produced, or sold has electronics records. Those records may not be perfect, but they are usually very accurate. If people fail at properly dealing with the data, it is not really the transactional data that is to blame. For a quantitative initiative to succeed, we need to fight the right battle. What is it that we are trying to deliver in the first place? One of the key deliverables for a quantitative supply chain is a core numerical recipe that computes the endgame supply chain decisions. This aspect was already discussed in the lecture 1.3 in the very first chapter, product-oriented delivery for supply chain. Let's revisit the two most critical properties of this deliverable. First, the output must be a decision. For example, deciding how many units to reorder today for a given SKU is a decision. On the contrary, forecasting how many units will be requested today for a given SKU is a numerical artifact. In order to generate a decision, that is the end results, many intermediate results are needed, that is many numerical artifacts. However, we must not confuse the mean with the end. And the second property for this deliverable is that the output must be, which is a decision, must be fully automated as a result of a purely automated software process, the numerical recipe itself, the core numerical recipe. Running the core numerical recipe must not involve any manual operation. Naturally, the design of the numerical recipe itself is likely to be heavily dependent on very human expert insights. However, the execution should not be dependent on direct human intervention. Having a numerical recipe as a deliverable is essential in order to make the supply chain initiatives a capitalistic endeavor. The numerical recipe becomes a productive asset that generates returns. The recipe must be maintained, but this requires 1 or 2 orders of magnitude fewer people compared to approaches that keeps humans in the loop at the micro decision level. However, many supply chain initiatives fail because they do not correctly frame supply chain decisions as the deliverable of the initiative. Indeed, those initiatives focus on delivering numerical artifacts instead. Numerical artifacts are intended to be ingredients to get to the final resolution of the problem, typically supporting the decisions themselves. The most common artifacts encountered in supply chain are forecasts, safety stocks, EOQs, KPIs. While those numbers can be of interest, they aren't real. Those numbers do not have an immediate, tangible, physical counterpart in the supply chain. They reflect arbitrary modeling perspective on the supply chain. Focusing on the numerical artifacts leads to failure of the initiative because those numbers are missing one critical ingredient: direct real-world feedback. When the decision is wrong, the bad consequences can be traced back to the decision. However, the situation is much more muddier as far as numerical artifacts are concerned. Indeed, the responsibility is diluted all over the place as there are many artifacts that contribute to every single decision. The problem is even worse when there are actually human intervention in the middle. Thus, this lack of feedback proved deadly for numerical artifacts. Modern supply chains are complex. Pick any arbitrary formula to compute a safety stock, an economic order quantity, or a KPI. There are overwhelming odds that this formula is wrong in all sorts of ways. The problem of the correctness of the formula isn't a mathematical problem. It is a business problem. It's about answering the question, does this calculation truly reflect the strategic intent that I have for my business? The answer varies from one company to the next. It even varies from 1 year to the next as companies evolve over time. As numerical artifacts lack direct real-world feedback, they lack the very mechanism by which it is possible to iterate from a naive, simplistic, and most likely widely incorrect initial implementation toward an approximately correct of the formula, version of the formula that could be deemed as production grade. Yet, numerical artifacts are very tempting because they give the illusion of getting closer to the solution. They give an illusion also of being rational, scientific even undertakings. We have numbers, formulas, algorithms, models. It is even possible to do benchmarks and compare those numbers with equally made-up numbers. And finally, improving against a made-up benchmark gives an illusion of progress as well. And it is very comforting, but at the end of the day, it remains an illusion, a matter of modeling perspective. Companies do not make profits by paying people to look at KPIs or doing benchmarks. They make profits by taking one decision after another and hopefully getting better at taking the next decision every single time. This lecture is part of a series of supply chain lectures. I'm trying to keep those lectures somewhat independent, but we have reached a point where it makes more sense to watch those lectures in sequence. This lecture is the very first lecture of the 7th chapter, which is dedicated to the execution of supply chain initiatives. And by supply chain initiatives, I mean quantitative supply chain initiatives that intend to deliver something that is order of a predictive optimization for the company. The very first chapter was dedicated to my views about supply chain, both as a field of study and as a practice. In the second chapter, I presented a series of methodologies which are essential to supply chain, as naive methodologies are defeated due to the adversarial nature of many supply chain situations. In the third chapter, I presented a series of supply chain personae. The emphasis was to a pure focus on the problems themselves. What is it that we are trying to solve? In the fourth chapter, I presented a series of fields which, while they are not supply chain per se, I believe that they are essential to a modern practice of supply chain. In the fifth and sixth chapters, I presented the smart bits of a numerical recipe intended to drive supply chain decisions, namely predictive optimization, which is like the generalized perspective of forecasting, and decision-making, which is essentially mathematical optimization, but applied to supply chain problems. In this seventh chapter, we discuss how to put those elements together in an actual supply chain initiative that intend to bring those methods and those technologies in production. Today, we will review what is considered as Lokad as the correct practice to conduct a supply chain initiative. This includes framing the initiative with the proper deliverable, which we just discussed, but also with the proper timeline, the proper scope, and the proper roles. Those elements represent the first part of today's lecture. The second part of the lecture will be dedicated to the data pipeline, a critical ingredient for the success of such a data-driven or data-dependent initiative. While the data pipeline is a fairly technical affair, it requires a proper division of labor, a proper organization between IT and supply chain. In particular, we will see that quality controls should be mostly in the hands of supply chain with the design of data health reports and data inspectors. The onboarding is the first phase of the initiative where the core numerical recipe, the one that generates the decision, along with all its supporting elements, is crafted. The onboarding ends with a progressive rollout into production, and during this rollout, the earlier processes get gradually automated away by the numerical recipe itself. When considering the appropriate timeline for the first quantitative supply chain initiative in the company, one could think that it very much depends on the company, that it depends on the size of the company, its complexity, the type of supply chain decisions, the overall context, all of that should be really factored into the timeline. Well, while it is true to a limited extent, the experience that Lokad has collected over a decade and dozens of such initiatives indicate that 6 months is almost invariably the appropriate timeline. And as surprising as it may be, this 6-month timeline has little to do with the technology or even the specifics of the supply chain. And it has a lot more to do with the people and the organizations themselves and the time it takes for them to get comfortable with what is typically perceived as a very different way of conducting supply chain. The first 2 months are dedicated to the setup of the data pipeline. We will be revisiting this point in a few minutes, but this delay of 2 months is caused by 2 factors. First, we need to make the data pipeline reliable and eliminate infrequent issues that may take weeks to manifest. And the second is that we need to figure out the semantic of the data. That is, to understand what the data mean from a supply chain perspective. And the months 3 and 4 are dedicated to the rapid iteration that are over the numerical recipe itself that will be driving the supply chain decisions. Those iterations are needed because generating actual endgame decisions is usually the only way to assess whether there is something wrong or not with the underlying recipe or all the assumptions that are built into the recipe. Those 2 months are also typically the time it takes for supply chain practitioners to get used to the very quantitative financial perspective that drive those decisions, so software-driven decisions. Finally, the last 2 months are dedicated to the stabilization of the numerical recipe after what is usually a relatively intense period of fast iteration. This period is also the opportunity for the recipe to run in a production-like setup, but not driving yet the production. This phase is important for the supply chain teams to gain trust in this emergent solution. While it could be desirable to compress this timeline further, it turned out that is typically very difficult. The setup of the data pipeline can be accelerated to some extent if the proper IT infrastructure is already in place, but gaining familiarity with data does not. I mean, it will take time to understand what the data mean, again, from a supply chain perspective, not from an IT perspective. And then, in the second phase, if the iteration over the numerical recipe converge very, very swiftly, then the supply chain teams are very likely to start exploring variants of the numerical recipe. And thus, again, that will kind of expand a little bit the delay, even if you can manage to compress it a little bit. And finally, the last 2 months is typically what it takes to see the seasonality unfold and gain trust. You know, again, it is very difficult to say that you will trust a piece of software to drive the, I would say, important supply chain decision in production after just a few days. And that's why, all in all, it takes kind of 6 months. And it's very difficult. While it would be desirable to compress it further, it is very difficult to do so. However, 6 months is already quite a sizable time frame. If from day one, the onboarding period, that is the period where the numerical recipe is not yet driving the supply chain decision, is from day one. This onboarding period is already expected to take more than 6 months. Then the initiative is already at risk. Indeed, if the extra delay is associated with the data extraction and the setup of the data pipeline, then there is an IT problem. We'll be revisiting the case in just a few minutes. If the extra delay is associated with the design or the configuration of the solution, then possibly brought by a third-party vendor, then there is a problem with the technology itself, and the technology doesn't fit, and that's why it takes longer. And finally, if after 2 months of stabilized production-like run, the production rollout do not happen, then there is typically a problem with the management of the initiative. When trying to introduce a novelty, a new process, a new technology into an organization, common wisdom indicates to start small and make sure it works and build upon this early success to gradually expand. Unfortunately, supply chain isn't kind to common wisdom, and this perspective comes with rather specific twist as far as supply chain scoping is concerned. In terms of scoping, there are two main driving forces that largely define what is and what is not an eligible scope as far as a quantitative supply chain initiative is concerned. The applicative landscape is the first force that impacts scoping, as supply chain as a whole cannot be observed directly. It can only be observed indirectly through the lenses of enterprise software. Indeed, the data will be obtained through those pieces of software. The complexity of the initiative greatly depends on the number and of the diversity of those software pieces. Indeed, each app is its own data source, and extracting and analyzing the data from any given business app tend to be a significant undertaking. Dealing with more apps usually means dealing with multiple database technologies, dealing with inconsistent terminologies, inconsistent concepts, etc. It vastly complicates the situation. Thus, when establishing the scope, we must acknowledge that the eligible frontiers, the eligible boundaries, are usually defined by the business apps themselves and their database structure. In this context, starting small must be understood as keeping the initial data integration footprint as small as possible while preserving the integrity of the supply chain initiative. As a rule of thumb, it is better to go deep rather than wide in terms of app integration. Once you have the IT plumbing in place to get some record from a table in a given app, it is usually straightforward to get all the records from this table and all the records from another table from the same app. One common scoping mistake consists of sampling the data. Sampling is usually achieved through picking a short list of product categories or a short list of sites, a short list of suppliers. Sampling is well-meaning, but it does not follow the boundaries as defined by the applicative landscape. To implement sampling, filters have to be applied during the data extraction. Indeed, because we don't want all the data by definition, we want a sample. And this process of sampling creates a whole series of issues that are likely to endanger the supply chain initiative. First, a filtered data extraction from a piece of enterprise software requires more effort from the IT team as opposed to an unfiltered extraction. Indeed, those filters have to be engineered in the first place as opposed to not having any filter in the first. Furthermore, the filtering process itself is error-prone, and as filters can be incorrectly defined. Debugging incorrect filters is invariably tedious because it requires numerous exchanges with the IT teams, and this will slow down the initiatives, which in turn endanger the initiative. Second, letting the initiative perform its onboarding of a data sample is a recipe for massive software performance issues as the initiative expands at a later stage toward the full scope. Indeed, poor scalability, that is an inability to process a large amount of data while keeping the computing cost under control, is a very frequent defect in software. By letting the initiative operate over a sample, scalability problems are masked. Those problems invariably come back with a vengeance at a later stage. And third, operating over a data sample makes statistics more difficult, not easier. Indeed, having access to more data is probably the easiest way to improve the accuracy and the stability of almost all machine learning algorithms. Sampling the data goes exactly against this insight. Thus, when using a small data sample, the initiative may fail due to erratic numerical behaviors observed over the sample dataset, while those behaviors would have been largely mitigated if the entire dataset had been used instead. System effects are the second force that impacts scoping. A supply chain is a system, and all its parts are coupled to some extent. The challenge with systems, any system, is that attempts at improving a piece of the system tend to displace problems rather than fixing anything. For example, let's consider an inventory allocation problem for a retail network. Let's assume that this network has one distribution center and many stores. If we pick a single store as the initial scope for our inventory allocation problem, then it is trivial to ensure that this one store will get a very high quality of service from the distribution center. We just have to reserve the inventory for this store ahead of time. By doing that, we can ensure that the DC will never run out of stock while serving this one store. However, this reservation of stock would be done at the expense of the quality of service for the other stores of the network. Thus, when we are considering a scope for supply chain of interest, we must consider the system effects. The scope should be designed in a way that largely prevents performing a local optimization at the expense of the elements that are outside the scope. This part of the scoping exercise is difficult because all scopes are leaky to some extent. For example, all parts of the supply chain ultimately compete for the same amount of cash that is available at the company level. Every dollar allocated somewhere is a dollar that won't be available for other purposes. Needless to say, or nevertheless, certain scopes are much more easily gamed than others. Thus, it is important to pick a scope that attempts to mitigate the system effects as opposed to magnify them. Thinking the scoping of a supply chain initiative in terms of system effects might feel a bit odd for many supply chain practitioners. When it comes to scoping, most companies are inclined to project their own internal organization onto the scoping exercise. Thus, the boundaries chosen for the scope invariably tend to mimic the boundaries of the division of labor that is in place in the company itself. This pattern is known as the Conway's law. This law was proposed by Melvin Conway half a century ago. At the time, the law was proposed with a relatively narrow focus for communication systems, but the law turned out to have a much broader applicability well beyond communication system. This law is actually of prime relevance for supply chain. The boundaries, the silos that dominate in present-day supply chains are driven by a division of labor that is the consequence of the fairly manual processes that are in place to drive the supply chain decisions. For example, if a company assesses that a supply and demand planner cannot manage more than 1,000 SKUs, then if the company has 50,000 SKUs to manage overall, then the company will require 50 supply and demand planners to do so. Yet, splitting the optimization of the supply chain into or across 50 pairs of hands is guaranteed to introduce many inefficiencies at the company level. On the contrary, an initiative that automates those decisions does not need to cater for those boundaries that only reflect, I would say, an obsolete or soon to be obsolete division of labor. A numerical recipe can optimize those 50,000 SKUs at once and eliminate all the sort of inefficiencies that were the results of having dozens of silos pitted one against each other. Thus, it is only natural for an initiative that intends to vastly automate those decisions to overlap with many pre-existing boundaries in the company. The company, or actually the management of the company, must resist the urge to mimic the existing organizational boundaries, especially at the scoping level, as it tends to set the tone for what follows. Supply chains are complex in terms of hardware, software, and people. While it is unfortunate, starting a quantitative supply chain initiative further increases the complexity of the supply chain, at least initially. On the long term, it can actually substantially decrease the complexity of the supply chain, but we'll get to that probably in a later lecture. Furthermore, the more people there is involved in the initiative, the greater the complexity of the initiative itself. And if this extra complexity is not immediately put under control, then the odds are high that the initiative will collapse under its own complexity. Thus, when thinking about the roles of the initiative, that is, who is going to do what, we need to think about the smallest possible set of roles that makes the initiative viable. By minimizing the number of roles, we minimize the complexity of the initiative, which in turn greatly improves its odds of success. This perspective tends to be counterintuitive for large companies that love operating with an extremely thin-grained division of labor. Large companies tend to favor extreme specialists that do one thing and one thing only. However, supply chain is a system, and like all systems, it is the end-to-end perspective that matters. Based on the experience acquired at Lokad at conducting this sort of initiative, we have identified 4 roles that usually represent the minimal viable division of labor to conduct the initiative. That is a supply chain executive, a data officer, a supply chain scientist, and a supply chain practitioner. The role of the supply chain executive is to support the initiative so that it can happen in the first place. Getting a well-designed numerical recipe to drive the supply chain decision in production will represent a massive boost both in terms of profitability and productivity. However, it is also a lot of change to digest. It takes a lot of energy and support from the top management for such a change to happen in a large organization. And the role of the data officer is to set up and maintain the data pipeline. The bulk of its contribution are expected to happen within the first 2 months of the initiative. If the data pipeline is correctly engineered, there is very little ongoing efforts for the data officer afterward. The data officer is typically not involved much in the later stages of the initiative. And then the role of the supply chain scientist is to craft the core numerical recipe. This role starts from the raw transactional data as made available by the data officer. No data preparation is expected from the data officer, only data extraction. The supply chain scientist's role ends with taking ownership of the generated supply chain decision. It is not a piece of software that is responsible for those decisions. It is the supply chain scientist. For every generated decision, the scientist himself or herself must be able to justify why this decision is adequate. Finally, the role of the supply chain practitioner is to challenge the decision generated by the numerical recipe and to provide feedback to the supply chain scientist. The practitioner has the know-how to take the decision. This person has typically been in charge of those decisions so far, at least for a subscope, and usually with the help of spreadsheets and the help of systems in place. In a small company, it is possible to have one person fulfilling both the role of the supply chain executive and of the supply chain practitioner. It is also possible to bypass the need for a data officer if the data is readily accessible. This might happen in companies that are very mature as far as their data infrastructure is concerned. On the contrary, if the company is very large, it is possible to have a few, but only a tiny few people filling each role. The successful rollout in production of the core numerical recipe has quite an impact on the role of the supply chain practitioner. Indeed, to a large extent, the point of the initiative is to automate away the previous job of the supply chain practitioner. However, this does not imply that the best course of action is to fire those practitioners once the numerical recipe is in production. We will be revisiting this specific aspect in the next lecture. Being organized doesn't mean being efficient or being effective. There are roles that, despite being well-intentioned, add friction to supply chain initiatives, frequently to the point of making them fail altogether. Nowadays, the first role that contributes the most in making such initiative fail tend to be the role of the data scientist, and even more so when a whole data science team is involved. By the way, Lokad learned this the hard way about a decade ago. Despite the name similarity between data scientist and supply chain scientist, the two roles are actually very, very different. The supply chain scientist cares first and foremost about delivering real-world production-grade decisions. If this can be achieved with a semi-trivial numerical recipe, even better. Maintenance will be a breeze. The supply chain scientist takes the full responsibility of dealing with the most minute detail of the supply chain. Reliability and resilience to ambient chaos matter more than sophistication. On the contrary, the data scientists focus on the smart parts, on the smart bits of the numerical recipe, the models, the algorithms. The data scientist, and again, I'm speaking, I would say, in general terms, perceives himself or herself as an expert in machine learning and an expert in mathematical optimization. In terms of technologies, the data scientist is willing to learn the latest bleeding edge open source numerical toolkit, but this person is typically unwilling to learn about the 3-decade-old ERP that happens to run the company. Also, the data scientist isn't a supply chain expert, nor usually willing to become one. the data scientist attempts to deliver the best results according to agreed upon metrics. The data scientist has no ambition to deal with the very mundane details of the supply chain. Those elements are expected to be handled by other people. Although data science spells the doom of those initiatives because as soon as data science is involved, supply chain isn't the focus anymore. Algorithms and models are the focus. Never underestimate the power of distraction of the latest model, the latest algorithm that the latest model or the latest algorithm represent for a smart, technologically minded person. The second role that tends to add friction to a supply chain initiative is the business intelligence team. While when the BI team is part of the initiative, they tend to be a hindrance rather than anything else, although to a much lesser extent than the data science team. The problem with BI is that it's mostly cultural. BI deliver reports, not decisions. The BI team is typically willing to produce endless walls of metrics as requested by every single division of the company. This is not the right attitude for a quantitative supply chain initiative. Also, business intelligence as a piece of software is a very specific class of data analytics geared around cube or hypercube that let you slice and dice. Like most, I would say, in-memory systems, enterprise system, this design is usually quite unfit to drive supply chain decisions. Now that we have framed the initiative, let's have a look at the wide, high-level IT architecture that the initiative requires. The schema, let's directly move forward. The schema on the screen illustrates a typical data pipeline setup for a quantitative supply chain initiative. In this lecture, I am discussing a data pipeline that does not support low latency requirements. We want to be able to complete a full cycle in about 1 hour, not 1 second. Most supply chain decisions, like purchase order, do not require a low latency setup. Achieving end-to-end low latency requires a different kind of architecture, which is beyond the scope of today's lecture. The transactional system represents the ERP, the WMS, the MRP, the e-commerce platforms, all those systems that are used to operate the supply chain. The data lake represents a mirror of all the data contained in those transactional systems. The whole point of the data lake is to be a data servicing layer. The analytical system are the place where the core numerical recipe that generates the supply chain decision is implemented. Those systems also offer reporting capabilities. The decision integration module represents a staging layer that ensures a smooth integration of the decision into the transactional system. Decision integration does not need to be implemented at the very beginning of the initiative. As a rule of thumb, this implementation is part of the pipeline, is a part of the pipeline that can be delayed by 3 to 4 months after the kickoff of the initiative. Even when the business does not require to access to the data on a daily basis, as it can happen when everything is scheduled on a weekly basis, for example, I still strongly advise to have the data pipeline running in full at least once a day. Indeed, frequently running the data pipeline is the key to observe infrequent issues and fix them. Sticking to a schedule that is at least daily is a critical ingredient to achieve a decent reliability. The transactional systems represent the primary data source and the starting point of the data pipeline. Those systems include the ERP, the WMS, the EDI. Those systems deal with the flow of goods, such as purchasing, transport, production, selling. Those systems contains almost all the data that the core numerical recipe requires. For practically any sizable company, those systems or their predecessors have been in place for 2 decades at least. As those systems contains almost all the data that we need, it would be tempting to actually engineer the numerical recipe directly into those systems. Indeed, why not? By putting the numerical recipe right into the ERP, we would remove the need to go through the effort of setting up this entire data pipeline. Unfortunately, this does not work due to the very design of those transactional systems. Those transactional systems are invariably built with a transactional database at their core. This approach for the design of enterprise software has been exceedingly stable for the last 4 decades. Pick any random company, chances are that every single business app in production has been implemented on top of a transactional database. Transactional databases offer 4 key properties that are known under the acronym ACID, which stands for atomicity, consistency, isolation, and durability. I'm not going to delve, at least not today, in the fine print of those properties, but suffice to say that those properties makes the database very suitable to perform safely safely and concurrently many small read operations and many small write operations. The respective amounts of read operations and write operation is also expected to be fairly balanced. However, the price to pay for those very useful ACID properties at the most granular level is that the transactional database is also very inefficient when it comes to servicing big read operations, a read operation that covers a sizable portion of the entire database. As a rule of thumb, if the data is serviced through a database that focuses on a very granular delivery of those ACID properties, then you can expect the cost of the computing resources to be inflated by a factor 100 compared to architecture that don't focus as much on those ACID properties at such a granular level. ACID is nice, but it comes at a massive premium. Moreover, when someone attempts to read a sizable portion of the entire database, the database is likely to become unresponsive for a while it dedicates the bulk of its resources to servicing this one big request. Many companies complain that their entire business systems are sluggish, that those systems frequently freeze for 1 second or more. Usually, this poor quality of service can be traced back to heavy SQL queries that attempt to read too many lines at once. And therefore, the core numerical recipe cannot be allowed to operate in the same environment that the transactional system that support production. Indeed, numerical recipe will need to access most of the data whenever it is run. Thus, the numerical recipe must be kept strictly isolated into its own subsystem, if only to avoid degrading further the performance of those transactional systems. By the way, while it has been known for decades that it is a terrible idea to have a data-intensive process operating within a transactional system, this does not prevent most vendors of transactional systems, ERP, MRP, WMS, from selling integrated analytical modules, for example, inventory optimization modules. Having those modules integrated inevitably lead to quality of service problems while delivering underwhelming capabilities. All of those problems can be traced back to this single design problem. The transactional system and the analytical system must be kept in strict isolation. The data lake is simple. It is a mirror of the transactional data geared toward very large read operations. Indeed, we have seen transactional systems optimized for many small read operations, not very large ones. Thus, in order to preserve the quality of service of the transactional system, the correct design consists of carefully replicating the transactional data into another system, namely the data lake. This replication must be implemented with care precisely to preserve the quality of service of the transactional system. Which typically means reading the data in ways that are very incremental and to avoid to put spikes of pressure on the transactional system. Once the relevant transactional data is mirrored into the data lake itself serves all the data requests. And additional benefits of the data lake is to be able to serve multiple analytical systems. Indeed, while we are discussing supply chain here, if marketing want their own analytics, they will need this very same transactional data. And the same could be said for finance, for sales, etc. Thus, instead of having every single department in the company implementing their own data extraction mechanism, it makes sense to consolidate all those extraction into the data lake, into the same data lake, the same system. At the technical level, a data lake can be implemented with a relational database, typically tuned for big data extraction, typically adopting a columnar data storage. A data lake can also be implemented as a repository of flat files served over a distributed file system. Compared to a transactional system, a data lake gives up on the fine-grained transactional properties. The goal is to serve a large amount of data as cheaply and as reliably as possible. Nothing more, nothing less. The data lake must mirror the original transactional data. Mirroring means copying without modifying anything. It is important not to prepare the data in the data lake. Unfortunately, the IT team in charge of a setup of the data lake can be or is usually tempted to make things easier and simpler for the other teams and thus to prepare the data a little bit. However, modifying the data invariably introduces sorts of complications that undermine analytics at a later stage. In addition, sticking to a strict mirroring policy vastly diminishes the amount of efforts needed for the IT team to set up and later maintain the data lake. In companies where there is already a BI team in place, it can be tempting to use the BI systems as a data lake. However, I strongly advise doing so and never use a BI setup as a data lake. Indeed, the data in BI system, business intelligence system, the data is invariably heavily transformed already. Leveraging the BI data to drive automated supply chain decision is a recipe for garbage in, garbage out problems. The data lake must only be fed from primary data sources like the ERP, not from secondary data sources like the BI system. The analytical system is the one that contains the core numerical recipe. It is also the system that provides all the reports that are needed to instrument the decisions themselves. At a technical level, the analytical system contains the smart bits, like the machine learning algorithm and the mathematical optimization algorithms. Although in practice, those smart bits are not dominating the code base of the analytical systems. Usually, data preparation and data instrumentation takes at least 10 times as many lines of code as the parts that are dealing with learning and optimization. The analytical system must be decoupled from the data lake because those two systems are completely at odds in terms of technological perspective. As a piece of software, the data lake is expected to be very simple, very stable, and extremely reliable. On the contrary, the analytical system is expected to be sophisticated, under constant evolution, and extremely performant as in supply chain performance. Unlike the data lake that must deliver near perfect uptime, the analytical system does not even have to be up most of the time. For example, if we are considering daily inventory replenishment decisions, then the analytical system only has to run and be up once per day. As a rule of thumb, it's better to have the analytical system fail at producing decision rather than generating incorrect decisions and letting them flow into production afterward. Delaying supply chain decisions by a few hours, like purchase orders, is typically much less dire than taking incorrect decisions. As the design of the analytical system tends to be heavily influenced by the smart bits that it contains, that is not necessarily that much to be said in general about the design of the analytical system. However, there is at least one key design property that must be enforced for the analytical system. It's namely that this system must be stateless. The analytical system must try to avoid having an internal state to the greatest extent possible. Thus, in other words, the analytical system must start with the data as presented by the data lake and end with the generated intended supply chain decision supporting the reports. Yet, what happens is that whenever there is a component inside the analytical system that is too slow, like a machine learning algorithm, it is tempting to introduce a state, that is to persist some information from the previous execution in order to speed up the next execution. However, doing so, relying on previously computed results, as opposed to recompute everything from scratch every single time, is dangerous. Indeed, having a state within the analytical systems puts the decision at risk in the sense that while data issues, and there will be data issues, get fixed at the data lake level, the analytical system may still return decisions that are still reflecting a problem that has already been fixed. For example, if demand forecasting model is trained over a corrupt sales data set, then the forecasting model remains corrupt until this model is retrained over a fresh corrected version of the dataset. The only way to avoid the analytical system to suffer from echoes of data issues that have already been fixed in the data lake is to refresh everything every time. That is the essence of being stateless. As a rule of thumb, if a part of the analytical system proves to be too slow to be refreshed daily, then this part must be considered as suffering from a performance problem. Supply chain is chaotic, and there will be a day when something happens, a fire, a lockdown, a cyber attack, which will require an immediate intervention. The company must be able to refresh within 1 hour all its supply chain decisions. The company must not wait and be stuck for 10 hours while the slow machine learning training phase is taking place. In order to operate reliably, the analytical system must be properly instrumented. That is what the data health reports and the data inspectors are about. And by the way, all those elements are the responsibility of the supply chain. Those elements are not the responsibility of IT. Data health monitoring represents the very first data processing phase, even before the data preparation per se. And it happens within the analytical system. Data health is a part of the instrumentation of the numerical recipe. The data health report indicates whether it is acceptable or not to run the numerical recipe at all. This report also pinpoints the origin of the data problem, if any, in order to speed up the resolution of the problem. Data health monitoring is a practice at Lokad. During the last decade, this practice has proved to be invaluable in order to avoid garbage in, garbage out situation that seems to be ubiquitous in the world of enterprise software. Indeed, when a data crunching initiative fails, bad data is frequently put to blame, but I can't help to notice that usually there is almost no engineering effort whatsoever to enforce the data quality in the first place. data quality does not fall from the sky. It takes engineering efforts. The data pipeline that has been presented so far is pretty minimalistic. Data mirroring is as simple as it can get, which is a good thing as far as software quality is concerned. Yet, despite this minimalism, there are still many moving parts, many tables, many systems, many people. Thus, there are bugs all over the place. I mean, this is enterprise software. The contrary would be quite surprising. Data health monitoring is the place to help the analytical systems to survive the ambient chaos. Data health should not be confused with data cleaning. Data health is only about to make sure that the data that is made available to the analytical system is, I would say, a faithful representation of the transactional data that exists in the transactional systems. There is no attempt at fixing the data. The data is analyzed as is. At Lokad, we typically distinguish low-level data health from high-level data health. The low-level data health is a dashboard that consolidates all the structural and volumetric oddities of the data. That is, the obvious problems such as entries that are not even reasonable dates or numbers, for example, or orphan identifiers that are missing their expected counterparts. All those problems that can be seen in the data. And the problem that can be seen on the data are actually the easy ones. The difficult problem starts with issues that cannot be seen in the data because data is actually missing in the first place. For example, if something went wrong with a data extraction and the sales data extract of yesterday only contain half of the line that one would normally expect, it can really endanger the production. Indeed, incomplete data is particularly insidious because it usually won't prevent the numerical recipe from generating decisions, except that those decisions are going to be garbage as the input data is incomplete. Technically, at Lokad, we try to keep the data health monitoring on a single dashboard, and this dashboard is typically intended for the IT team, as most of the problems that are captured by the low-level data health tend to be related to the data pipeline itself. Ideally, the IT team should be able to tell at a glance whether everything is okay or not, and whether no further intervention is required for them. High-level data health monitoring considering all the business-level oddities, elements that looks wrong when being observed from a business perspective. High-level data health covers elements such as negative stocks level or absurdly large minimal order quantities. It also covers things like prices that don't make sense because the company would be operating at a loss or operating with ridiculously high margins. High-level data health attempts to cover all the elements where the supply chain practitioner would look at the data and say, it can't possibly be right, we have a problem. Unlike the low-level data health report, high-level data health reports is primarily intended for the supply chain team. Indeed, problems like an anomalous minimal order quantities is only going to be perceived as a problem by a practitioner who is somewhat familiar with the business environment. Again, at the point of this report is to be able to tell at a glance that everything is okay, that no further intervention is required. Previously, I said that the analytical system was supposed to be stateless. Well, it turned out that the data health is the exception that proves the rules. Indeed, many problems that can be identified by comparing the present-day indicators with the same indicators collected over the previous days. Thus, the data health monitoring will typically persist some kind of stage, which are basically key indicators as observed over previous days, so that it can identify, I would say, outliers in the present state of the data. However, as data health is a pure matter of monitoring, The worst that can happen if there is essentially a problem at the data lake level that gets fixed, and then we have, I would say, echoes of the past problems in the state of the data hub. The worst that can happen is to get a series of false alarms from those reports. The logic that generates the supply chain decisions remains entirely stateless. The state only concerns a little part of the instrumentation. Data hub monitoring, both at the low level and high level, is a matter of trade-off between the risk of delivering incorrect decision and the risk of not delivering the decisions on time. When looking at a large supply chain, it is not reasonable to expect that 100% of the data will be correct. Incorrect transactional entries do happen even if they are rare. Thus, there must be a volume of issues that should be deemed as sufficiently low for the numerical recipe to operate. The trade-off between those two risks being oversensitive to data glitches or being too tolerant to data abuse depends heavily on the economic makeup of the supply chain. Thus, at Lokad, we craft and fine-tune those reports on a client-by-client basis. Indeed, instead of chasing every conceivable case of data corruption, the supply chain scientist, who is the one in charge, by the way, of implementing the low-level data hub, the high-level data hub, and the data inspectors that I will be discussing in a minute, tries to tune the data hub monitoring to be sensitive to the sort of problems that are actually damaging and actually happening for the supply chain of interest. In the Lokad jargon, a data inspector, or simply an inspector, is a report that consolidates all the relevant data concerning an object of interest. The object of interest is expected to be one of the first-class citizens from a supply chain perspective: a product, a supplier, a client, a warehouse. For example, if we are considering a data inspector for products, then for any given product sold by the company, we should be able to see through the inspector on a single screen all the data that is attached to this product. In the data inspector for products, there is effectively as many views as there are products, because when I say we see all the data, I mean all the data that is attached to one, let's say, barcode or part number, not to all products in general. Unlike the low-level and high-level data health report that are expected to be two dashboards that can be inspected at a glance, inspectors are implemented to address questions and concerns that invariably arise while designing and then operating the core numerical recipe. Indeed, in order to take a supply chain decision, it is not infrequent to consolidate data from a dozen of tables, possibly originating from multiple transactional systems. As the data is all over the place, when a decision looks suspicious, it is usually difficult to pinpoint the origin of the problem. There can be a disconnect between the data as seen by the analytical system and the data that exists in the transactional system. There can be a faulty algorithm that fails at capturing a statistical pattern in the data. There can be an incorrect perception, and the decision that is deemed suspicious might, in fact, be actually correct. In every case, the inspector is intended to offer the possibility to zoom into the object of interest. In order to be useful, inspectors must reflect the specificities both of the supply chain and of the applicative landscape. As a result, crafting inspectors is almost invariably a bespoke exercise. Nevertheless, once the job is done, inspectors represent one of the pillars of the instrumentation of the analytical system itself. In conclusion, while most quantitative supply chain initiatives are set to fail even before the date of their kickoff, it doesn't have to be that way. A careful choice of deliverable, of timeline, of scope, and of roles is necessary to avoid problems that invariably set those initiatives for failure. Unfortunately, those choices are frequently somewhat counterintuitive, as Lokad learned the hard way through 14 years of operation so far. The very start of the initiative must be dedicated to the setup of a data pipeline. An unreliable data pipeline is one of the surest ways to ensure that any data-driven initiative will fail. Most companies, even most IT departments, underappreciate the importance of a highly reliable data pipeline that doesn't require ongoing firefighting. While the bulk of the data pipeline, of the setup of the data pipeline, falls to the hands of the IT department, supply chain itself must be responsible for the instrumentation of the analytical system it operates. Do not expect IT to do this for you. This one is on you, on the supply chain team. And we have seen two different types of instrumentation, namely the data health reports and that adopts, I would say, a company-wide perspective, and the data inspectors, which supports in-depth diagnostics. Today we discussed how to start an initiative, but next time we'll see how to end it, or rather, hopefully, how to bring it to production. In the next lecture, which will happen Wednesday, September 14th, we will move forward with our journey and see what sort of execution it takes to craft a core numerical recipe and then gradually bring the decision it generates to production. We will also have a closer look at what this new way of doing supply chain implies for the day-to-day operation of the supply chain practitioners. Okay, let's have a look at the questions. Okay, so a question from Chris Peterson. Why is it exactly 6 months is a time limit after which an implementation is not done correctly? I would say the problem is not really having 6 months as, I would say, as a time limit. It is that usually, as I was describing, initiatives are set up to fail from the get-go. That's the problem. And if your predictive optimization initiative starts with the perspective that results will be delivered, that it will take 2 years to get to the point where you get results, I mean, in my experience, it is almost a guarantee that that basically the initiative will dissolve at some point and fail to actually deliver anything in production. You see, if I could, I would really prefer to have the initiative succeed in like 3 months. But as I said, essentially 6 months represent kind of the minimal timeline, in my experience, to get such an initiative to production. Any, I would say, extra delay increase the risk of having the initiative to fail. So I would very much have this initiative compressed further. The problem is that it is very difficult because once you've kind of solved all the technical problems, all the delays that remain have nothing to do with the technology. They are only reflecting, I would say, the time it takes for people to get into the motion of the initiative. And that's why it is very difficult to compress further this timeline. But make no mistakes, 6 months is already quite long, and just this delay alone introduce a very certain amount of risk for the initiative. So if from day one you expect that it's going to take much longer, then you are already taking immense risk, and that is the crux of what needs to be addressed. A second question from Chris Peterson. Supply chain practitioners may get frustrated with an initiative that replaces the majority of their workload, such as the purchasing department in conflict with decision automation. How would you advise to handle this? So this is a very, very important question, which will be addressed, hopefully, in the next lecture. But for today, what I can say is I believe that most of what supply chain practitioners are doing in present-day supply chain is not very rewarding. I mean, if typically what happens in most companies is that people will get a slot of SKUs, or a slot of part numbers, let's say from 1,000 to 5,000, and then they will endlessly cycle over this loop, taking all the decision that needs to be taken. But that means that basically your job is to look at a spreadsheet and cycle through the spreadsheets once a week or possibly once a day. This is not, I would say, a very fulfilling job. So the short answer is that the way Lokad approaches the problem is that by automating all the mundane aspects of the work, so that the people in place that have actually genuine expertise in the supply chain can actually start challenging the fundamental of the supply chain, try to discuss more with the client, try to discuss more with the suppliers, try to discuss more so that everything can be more efficient. So it's really about collecting all the insights so that we can actually improve the numerical recipe, but executing the numerical recipe is super tedious, and the sort of jobs where I believe that a couple of decades from now, when it's finally acknowledged that those sort of things have to be automated, there will be very few people that regret the good old times where they had to cycle through every single day, 8 hours a day over the same spreadsheet. A question from Alexei Tikhonov. Are supply chain practitioners expected to work with all kind of data health reports in order to challenge the decision generated by supply chain scientists? Supply chain practitioners are expected to work with data inspectors, not data health reports. Data health reports is really like a company-wide assessment of that answers the question which is the collection of data that I have at the entrance of my analytical system, is it good enough to have a numerical system or a numerical recipe operate on top of the data set? So it's basically the outcome of the data health report is basically a binary decision, green light the execution of the numerical recipe, or pause and say we have a problem here that needs fixing. So this is what the data health is about. However, indeed, the data inspector, and again, it will be discussed more in the next lecture, are really the entry point for the supply chain practitioners to kind of, I would say, get insights about a proposed supply chain decision, because usually the supply chain practitioners themselves are struggling in consolidating all the relevant data in one place. You see, typically, the reason why they operate also with spreadsheets, it's because the data is split over multiple different systems, and the only way to get a consolidated view that lets you decide on a supply chain decision, like, for example, a production order or purchase order, is to bring all those data together. So the inspector, this is really the primary purpose of the inspector, is to be able to consolidate all those relevant data for one given product, for one given client, for one given supplier, so that we can reason about a specific decision. Another question asked from Operation Science. Is it feasible to update an analytical model, for example, setting an inventory policy on a daily basis? The supply chain system cannot respond to daily policy change. Won't it just feed noise to the system? I mean, so is it feasible to update, so to the first part of the question, is it feasible to update an analytical model on a daily basis? Yes, certainly it is. For example, Lokad, when we were operating in 2020 with the lockdowns taking place in Europe, I mean, we had with like 24 hours of I would say of headway for the notice. We had countries in Europe that were like closing or reopening again. So it was an extremely chaotic situation that was where constant immediate revisions were needed literally on a daily basis. And we did operate with this kind of, I would say, extreme amount of pressure, having lockdowns that were starting or ending on a daily basis across Europe for almost 14 months. So is it feasible? Yes. Is it desirable? Well, not necessarily. But the reality is that when you say the supply chain system cannot respond to daily policy change, it is true that supply chain as a system has a lot of inertia. And the first thing that an appropriate numerical recipe is must acknowledge is the fact that most decisions have a ratchet effect. Once you have ordered a production to take place, the raw materials are consumed. You cannot undo your production and say, I would like to get back my raw materials. Usually it's not possible. So there is like a ratchet effect with all of decision. And then when you take the next decision, you have to take into account the fact that there are plenty of things that are already, that have already been decided. However, when in the data you realize that your supply chain needs a drastic change in terms of its course of action, there is no point in delaying further this correction just for the sake of delaying the decision. You see, it's not because you have a lot of inertia that when there is a change that needs to happen, well, the best time to have this change happen is right now. I mean, because you can't do. It would even be preferable to have this change implemented in the past, but you can't do that. So the best alternative is just to do it now. And then when it comes to the noise aspect of the question, you see, again, it comes to the correct design of a numerical recipe. There are plenty of incorrect designs where when you say you have noise, essentially you're looking at classes of numerical recipes that are very unstable. And thus, very small changes in the data generate, I would say, very large change in the decisions that are in the, I would say, that represent the outcome of the numerical recipe. I mean, it is a problem. A numerical recipe should not be jumpy whenever there is like a little fluctuation in I would say, in the supply chain. And by the way, this is the reason why Lokad, for example, adopted this predictive, this probabilistic, perspective on the forecast. It's because once you adopt, a probabilistic perspective on the forecasting side, your models suddenly are much more, can be engineered to become much more stable compared to models that really try to capture the mean and that try to be very jumpy whenever there is like an outlier that happen in the supply chain. For example, when you have an outlier, if you have like a probabilistic perspective, it's going to slightly update, the probability of having such an outlier happening in the first place. But all in all, it's not going to radically reshape your probability distribution. On the contrary, if you're trying to collapse the entire forecast into a single number, which is the case when you're doing like a classical deterministic forecast, then the forecast tends to be very sensitive to outliers. And if you do, let's say, robust statistics, for example, using the median, then you end up with very weird situation where, for example, your forecast is stuck at 0 because the most frequent values that you see in your supply chain is 0, and that doesn't really make sense either. Another question from Vikas Verma. One of the problems we face in supply chain with very large companies is their dependency on different source systems. It is extremely difficult to bring the data from all the source systems into, isn't it extremely difficult to bring all data from all source systems under one unified system? So I completely agree that getting all the data is a very large challenge for many companies. But we must really ask ourselves the question, why is it a challenge in the first place? As I said, 99% plus of the business apps operated by large companies nowadays rely on, I would say, mainstream, well-engineered transactional database. You see, this is, I mean, there are still maybe a few super legacy COBOL implementation that runs on super, I would say, weird ad hoc binary storage, but this is rare. I mean, like the vast majority of the business apps, even business apps that were deployed like in the 90s, operate with a clean production-grade transactional database in the backend. So once you have a transactional backend, why should it be difficult to just copy this data toward the data lake? Most of the time, the problem is that companies don't just try to copy the data. They try to do a lot more. They try to prepare the data. They try to transform the data. They try to do a lot more than just mirroring the data, as I was just describing. You know, most modern database setup even have built-in data mirroring setup. So you can literally take, through journalization, you can literally take a transactional database and have all the data, all the changes that are brought to this relational database replicated into a secondary database. So, and this is like built-in properties for probably the top 20 most frequently used transactional systems in the market. So the sort of problems that companies have is at first they try to do too much, and thus they overdo it, and then the initiatives that is supposed to consolidate all the data just collapse under its own complexity, because it tried to do a lot more than just merely replicating the data. And then once data is consolidated, most companies tend to make the second mistake to think that crossing the data, connecting all those data together should be done by IT, or should be done by BI, or should be done by the data science team. So basically, it should be done by a division that is not directly in control of some kind of production. And the point that I would like to make here is that supply chain must be in charge of its own numerical recipes, just like the same that marketing must be in charge of its own numerical recipes, and the same for sales, extra, or finance. You see, it should not be like a transverse support division that tries to do that for the company, because if it's like a transverse division that tries to do that, connecting, for example, the data from two different systems requires typically tons of business insights. So large companies tend to fail because they try to have, I would say, an expert of coming from IT or from BI or from a data science team to try to do this job, while it should be done in the division of interest. Okay, I think this is all. Thank you very much for your time today, your interest, your questions, and see you next time after the summer in September.